Hi guys, we're going to do a little bit of work with some improper integrals here today. So something new for you guys, so I thought I'd do a video on it. It's talking about a topic that we're going to get into next semester for Calculus BC, dealing with convergence and divergence of series. And so I'm going to talk a little bit about that. If you could take some notes on this, I think it'll be helpful. But integrals with infinite limits of integration are improper integrals. Now, just because they have infinite limits of integration doesn't mean that they can't converge. In other words, you can't find the area underneath the curve. It's not finite. So an infinite limit of integration does not mean that it has to just keep building area. Some of them do, some of them don't. So we say if an integral has a value, that is, it approaches a real number, we say it converges. Otherwise, we say the improper integral diverges. All right. So let's look at example 1 here. You can pause the video as you need to, but we've got an integral from 2 to infinity of 3 over x minus 1 minus 3 over x dx. Now, proper notation, which I won't necessarily use, in upper level math, sometimes we'll just think in terms of infinities, which is fine, but infinity, remember, is a concept and not a number. So proper notation says that limit as b approaches infinity of the integral from 2 to b of 3 over x minus 1 minus 3 over x dx is how we should write this. So write as the limit of the integral with b on there instead of infinity. We're going to break this thing up. So we have the limit as b approaches infinity of the integral from 2 to infinity of 3 over x minus 1 minus the limit as b approaches infinity of the integral from 2 to infinity, or 2 to b, sorry, of 3 over x. Slap on a dx on each of those. Dx here too. Integrate each piece. So we've got the limit as b approaches infinity of 3 ln, the absolute value of x minus 1. That's going to be evaluated from 2 to b. Or wait to put that evaluation marker in there. And then we'll just do this minus 3 ln, absolute value of x. And our evaluation is from 2 to b here. So get the limit as b approaches infinity of 3 ln of x minus 1 minus 3 ln of x. We're going to want to go ahead and use the properties of a natural log of ln to write as a single expression. So it'll look like this. It's limit as b approaches infinity. You're going to do this over and over again. Of 3, and then we've got ln of the absolute value of x minus 1 over x. Because log of a minus log of b is log of a over b. We're going to evaluate that thing from 2 to b. So when I plug this in, plug in b, I've got the limit as b approaches infinity of 3 ln, absolute value of b minus 1 over b, and then it's going to be minus, by the fundamental theorem of calculus, 3 ln of absolute value of 2 minus 1 over 2. Evaluate the limit. So let's go ahead and evaluate this limit. We've got this guy right here, ln, as b approaches infinity, we essentially have b over b here, or 1, infinity over infinity, if you will, which is 1. 3 ln of 1 is going to be 0, so this whole thing is approaching 0 as b approaches infinity. So I've got 0 minus 3 ln absolute value of 1 over 2. You could drop the 1 over 2 for the absolute value. You got negative 3 ln of 1/2. You can just leave it like that. There's other ways you could write it, but that's a real number. It converges because the area under the curve equal the real number, and so that's it. So there is an improper integral example. I want to show you one that diverges, and then other than that, it's just applying all the different techniques of integration and then evaluating the limit as b approaches infinity of that thing. Or like I said, I'll show you on the next one. That's the way I think about it. But example 2 here, it says the integral from 1 to infinity of 1 over x dx. So we can rewrite that if we want to. The way I think about it, though, is it's just ln of absolute value of x evaluated from 1 to infinity. We really should think of it in terms of a limit, but we got, you know, if you wanted to, you could write this as limit as b approaches infinity of ln of absolute value of x from 1 to b. But thinking about this up here, we've just got ln of some really big number, infinity, minus ln of 1. Ln of infinity is just going to keep growing. If you think about the graph of it, it grows slowly, but it's just going to keep growing. But just the curve just keeps growing slowly. And then ln of 1 is 0. So the fact that ln of infinity just keeps growing, even though it grows slowly, it says that this thing is going to equal infinity, and so it diverges. That's it. That's one example of one that diverges, one that converges. Honestly, in terms of what you need to do, this is use partial fractions. So we're going to be reviewing partial fractions. Maybe we can do this one just to review it. The idea of partial fractions might help you. Here's the method of partial fractions. See if you remember this. We're going to take 2 over x squared plus 4x plus 3. We're going to rewrite that. That equals 2 over x plus 3, x plus 1. Then what we're going to do is clear fractions by multiplying both sides through. Oh, before we do that, we're going to break this up into two things. So we have this 2 over x plus 3 times x plus 1 has to equal some number a over x plus 3 plus some number, let's call it b, over x plus 1. And what we're trying to do is find the coefficients that when we get common denominators and add them together, you get a 2 on the top. So we're just breaking this single fraction up into 2 fractions. So it's like working backwards from what you did in Algebra 1. But we need to do that so that we have 2 ln forms here and here when we go to integrate it. And we just need to know those coefficients a and b. So if I multiply each side by the bottom of the left-hand side, I end up with 2 equals a times x plus 1. I think you'll start to remember this as you see me do it, plus b times x plus 3. And then we're going to go ahead and equate coefficients, solve for a and b. Let's see if we can do that. So we got 2 equals ax plus a plus bx plus 3b. So we've got a plus bx plus a plus 3b. Clearly over here, it's 0 is the coefficient of x, 2 is our constant, so a plus b has to equal 0, a equals negative b, a plus 3b has to equal 2, and so if I know a equals negative b plus 3b has to equal 2 by substitution, therefore b equals 1. B equals 1, a equals negative 1, and we are set to go ahead and rewrite this thing before we integrate it. So b equals 1, a equals 1. I don't need to go through that process again. I want to show you it one more time. So this is equivalent to the integral from 0 to infinity of, said a equals 1, I think. A equals negative 1, b equals 1. Okay, so negative 1 over x plus 3 plus 1 over x plus 1 dx. So now we've got the integral of each of these. We can separate it out. So integrate these things. We've got the integral from 0 to infinity of, let's skip that step. Let's just integrate this separate here. So we've got negative ln of x plus 3 plus ln of x plus 1 evaluated from 0 to infinity. We're going to join these two together here. We got negative ln. So, so we can rewrite this thing. We've got ln, negative sign out front. Maybe let's think of it this way. Just ln of absolute value, put the positive 1 on top, x plus 1. Let's see. And so we're going to think of this as like ln of a minus ln of b. So it's ln of x plus 1 over x plus 3. That was on the bottom now. Evaluated from 0 to infinity. So we got to think of what's happening here. As I plug in infinity, I've got infinity over infinity, or ln of 1. So the first term is going to be 0 minus ln of, plug in the 0, I get ln of 1/3. I can drop the absolute value, so that's a positive 1/3. So I get negative ln of 1/3. So that's what this thing converges to. We use the method of partial fractions on that thing, which is in this unit. So there's your review of partial fractions, how to set that up. You get the two factors, and then you write each distinct factor over underneath a different letter. By the way, if we had had 3 factors, you'd have an a, b, and a c. If you had like a squared on here, you would have another factor. It would be a plus c over x plus 1 squared. You have to have each factor represented up to its highest power. And so you have to have, if it was third power, you'd have to have one of each. But you have, if that were squared, you'd have a plus c over x plus 1 squared in there as well. It's not squared, so we don't need this. I don't remember if I did any of those on there, but that's the idea of the method of partial fractions. So I believe I have a video on that as well on my website if you want to look up partial fractions and review that we did last year. So one more here. This is integration by parts. So this will be your review of integration by parts. We're going to do an improper integral. So what we're doing with improper integrals, you can do with definite integrals. We're just looking at the limit as b approaches infinity for these. So integration by parts, it says we're going to get our u v minus integral of d du. We're going to rewrite this. We've got to pick a u. We've got to pick a dv. We've got to get a v. And we've got to get a du. So what I explained last year is we want to pick for our u something like the polynomial function that's going to, as you take the derivative, work down towards a constant. So u is equal to x. Du is equal to 1 dx. dv is going to be e to the negative x. Integral of that is going to be negative e to the negative x. So plugging this in here, we've got, and we'll just treat it like an indefinite integral for now. We've got uv, so it's x, negative x e to the negative x minus integral of v, which is negative e to the negative x, du, which is 1 dx. And so this becomes negative x e to the negative x plus the integral of e to the negative x dx. These two negative signs here. So you got negative x e to the negative x minus e to the negative x. Now let's go ahead and evaluate it from 1 to infinity. Remember, this should be a b up here at the top. Limit as b approaches infinity. You need to write that out on the AP exam. Limit as b approaches infinity. We should do it now. Okay, limit as b approaches infinity of negative x e to the negative x minus e to the negative x, evaluated from 1 to b. And here's what I get. So I've got negative b e to the negative b minus e to the negative b minus negative 1 e to the negative 1 minus e to the negative 1. See what happens on this thing as b, limit as b goes to infinity. So limit as b goes to infinity. What's going to happen here? We've got negative b over e to the b minus 1 over e to the b. Each of these as b goes to infinity here and here. This is going to grow faster, so that thing will go to 0. This thing will go to 0. And then over here we've got minus, and then that's going to change signs there. So that becomes a 1 over e, so plus 1 over e, and then plus 1 over e, which is equal to 2 over e. So this thing converges, and it converges to 2 over e. So a little review of integration by parts, partial fraction decomposition, and the idea of convergent and divergent improper integrals. So everything you know about integrals works, and everything you know about limits works. You're just combining those two together. It's the perfect storm. Hope that was helpful.